Hi there, Andrew Dunkley here. Thanks for joining us on the latest edition of Space Nuts. Until next week when it won't be the latest edition. But anyway, we'll get there. Coming up on this episode, we're going to stick to the solar system. We're going to get very close to home and talk about my next door neighbour. No, not quite that close. But we're going to talk about the moon. It's now been discovered that it's older than we thought. Fred remembers that. And mapping ice on Mars. We're talking water ice. We will also be dealing with some questions from Paul about the James Webb Space Telescope. Rennie is asking about how you calculate travel time in space. And a question from Sweden. Why is astronomy important? I'll answer that one right now. Because. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to cover all of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew, and broadcaster at large yourself, too.
Broadcaster at large. Yeah, I'm getting larger. It's a problem when you go on cruise ships. They just tend to keep shoveling food in your face. It's I think they could solve third world hunger problems if they just sent cruise ships there. I reckon everything would be fine. Yeah.
One way of doing it.
But yes, otherwise fine. Now, let's get stuck straight into it, Fred, because there's a couple of interesting stories around, as always. There's always interesting stories in astronomy and space science. But this first one, very close to home, because the moon has been using some kind of face cream because it doesn't look as old as it really is. They've just discovered it's older than we thought.
Yeah, that's right. And we're now talking about, I guess, what you might call precision dating of the solar system. We've kind of narrowed down the birth of the solar system to around about 4.57, I think it is, billion years ago. And so, you're talking about that's hundreds of a billion, which is sort of tens of millions. So you've got we've got some nice accuracies being brought up. And just to recap, we've talked about this many times before. We think the moon originated in the early history of the solar system when the planets were sort of in their infancy. Remembering that the solar system started off as a protoplanetary disk, excuse me, a disk of material orbiting the infant sun, which was very dusty, had gas in it, and all of that came together to form the planets as we know them today by this process we call accretion, which is stuff sticking together and typically under its own gravity. So the planets at that time were very hot because the impacts, the bombardment of all the debris in this protoplanetary disk, the energy of those impacts actually went into warming up the protoplanets, and so most of the early solar system, a lot of these worlds, which we now think of as solid bodies, like the 4 rocky planets, were actually molten. They were what we might call lava worlds. They had molten surfaces.
Yeah.
And in the middle of this scenario, here's the Earth with its probably molten surface. Something comes along and smashes into it, and that then raises a cloud of debris, which eventually coalesces to form the moon. And as I've said many times before, we call that hypothetical body. You probably remember the name yourself, the thing that smashed into the Earth to form the moon.
Theia.
Yeah, that's it. Yeah, the mother of the moon in, I think it's Greek mythology.
That's the first time in my life I've ever remembered something.
No, I can vouch that that's not the case. I think I've heard you do it twice, actually.
It's true.
So the Okay, Dave. All right. Let's keep going with the story. So this was, it's very hard for us to imagine looking at the Earth and the Moon today, these two marvelous bodies that mean so much to us. To imagine a scenario where they were effectively molten bodies, but that's was certainly the case. It's how they both became spheres, because they were sufficiently soft that gravity could pull them into a spherical shape. It obviously took them a while to cool down.
Yeah.
But that's a key part of the process in understanding the age of these things, is actually when they stop being molten. And that's basically a lead into the story that we've got today, which actually comes from scientists at the University of Chicago and the Field Museum, which I think is also in Chicago. It's two very eminent planetary scientists who've done this work. This is not, somebody's mad hypothesis. This is real stuff. And what they reason is that if you can find crystals and you can somehow manage to date them, then the crystals only formed after the moon solidified. So what you're doing is you're giving yourself a sort of minimum age for these crystals, or for the origin of the moon, by measuring the time when these things actually crystallized, because that's more or less the same time. It probably wouldn't have stayed molten for very long, this lunar magma ocean, as they call it. And so what they've done is they've gone back to 1972 when Apollo 17 brought back samples of moon dust. Some part of that, is it 385 kilograms or so of stuff that came back from the moon with the Apollo astronauts. And they've reanalyzed some of the crystals that dust contains. And in particular, what they're looking at are crystals of zircon, which is mineral that's commonly found. But they've taken this 1972 sample and they've reanalyzed it using absolutely up-to-date techniques which weren't available in 1972, including a process called atom probe tomography. Well, tomography is looking at the shapes of things, or cutting things to see their shape. And we all know what it is because we've seen computer-assisted tomographs of our own bodies often. I have, certainly. But this is at the atomic level. And then they can combine that with something called radiometric dating. And what they're doing is actually looking at the atoms themselves inside these zircon crystals and measuring another property, Andrew, that's really important in this is the level of radioactive decay. That's how the old carbon-14 dating works. Yeah, because you're looking at how much of one isotope of carbon there is compared with another, and you know that one turns into another over time. And if you can measure the relative amounts, then you know when that was laid down. That's only operable for organic material like wood and bodies and things of that sort. But they're doing this with atoms, and yet. So that is the bottom line. The answer they come out with is from the age of those crystals, they suggest that the moon is at least 4.46 million years old, which is 40 million years older than we thought it was.
Wow, that's a huge number.
It is, yeah. And when you compare it with 4.57 billion years for the age of the solar system, it means that it was very, very early on in the history of the solar system that the moon was formed. The moon is a truly ancient body. It's something, it's nearly as ancient as me.
Yeah, well, it is old and grey, basically.
It's pretty bald in places as well.
It is very bald in places. I suppose the question for me, though, is if the moon is 40 million years older than we thought, does that mean the Earth is 40 million years older than we thought? Or is that not the same thing?
It probably does, actually. You've got two things here. You've got the formation of the Earth, and then this impact that caused the moon to be formed. So what this research is doing is specifically looking at when the moon cooled after that event. Now, it begs the question, did the Earth and moon cool at the same time? And actually, we think the moon cooled earlier than the Earth did, because we believe...
left the fridge open. No?
Yeah, that's right. Actually, that's a bad thing to do under any circumstances. But so one of the reasons why we believe the moon cooled earlier than the Earth is the fact that the moon has these extraordinary differences between the near side and the far side. So the near side has a thin crust, and it's got all the lava flows which we see as the Maria, the grey areas. The backside is nothing like that. It's mountainous, cratered. There's about one or two of these little grey areas, but they're nothing like as big as the ones on the side facing us. And we think that is because the tidal locking of the moon into the Earth, so that it always faced the Earth, took place very soon after the formation of the moon, because the two bodies were a lot closer together then than they are now.
Yeah.
And we think that Earth was still hot, still a magma world, and that is why the backside of the moon, which would be a cooler side, actually got a thicker crust, because the gases, the silicates that were sort of in vapor form, could condense more readily on the backside of the moon because it's actually cooler. And so what the suggestion is that those zircon crystals may well have formed earlier than similar things on the Earth, because the Earth was still molten at that time. So I don't think, having said the opposite of this at the beginning of this answer, I don't think you can necessarily draw any conclusions about the age of the Earth from what we're seeing on the moon. I suspect our understanding of the age of the Earth is still much the same, 4.57 billion years.
If you want to be really technical about it, everything's the same age, because it all sort of came into existence at the exact same moment at the flash of the Big Bang.
Well, that's certainly true. Yes, that's true. If you're going back to the deep past, but we're not doing that in this instance. We're going back to the shallow past, just the age of the solar system, a mere 4.57 billion years.
The comprehensible past.
Well, yes, that's right. In many ways, I think we understand the way the solar system originated a lot better than we understand the Big Bang.
Yeah, absolutely. Here's just a question that popped into my mind. When Theia hit the molten Earth and caused the moon to spit out, why didn't it get reabsorbed into the Earth?
So that's a great question. So basically, it's the energy of Theia, the impact energy, the kinetic energy. Theia was half the size of the Earth. It's a Mars-sized object. So that is one enormous cloud. And yes, you can well imagine a debris cloud, which, because that impact was so energetic, what it does is pushes the debris from it out faster than the escape velocity of the Earth. And so some of that stuff would indeed have gone off into space and become interstellar dust. But enough of it was put into orbit around the Earth that then there was time for that to gravitationally coalesce by the same accretion process that formed the Earth, but at a later stage to form the Moon. So it's a great question.
Yeah, and
it's all about the energy.
That impact's become crucial in the development of life on Earth, because if that hadn't happened, this would be a completely different planet, would it not?
It would, yeah, that's right. For a start, it wouldn't have a moon unless we'd captured another one. And the moon is thought to have stabilized the rotation of the Earth. The fact that the moon's a body with 1/80th of the mass of the Earth, that's quite high for a satellite compared with its parent body, when you think of things like Io compared with Jupiter, for example. So so that's like acted as a flywheel to stabilize the Earth's rotation, and that in itself has been instrumental in the evolution of life on Earth.
It's fascinating, isn't it? When you really think about it, that one thing in the whole history of the universe made us possible. How big would Earth be if Theia didn't hit us?
Yeah, it would be
Slightly bigger,
12,500 kilometers, like it is now, or 13,000 kilometers. Yeah, possibly. I mean, you're right to kind of highlight that, because it goes to the heart of one of the problems that has faced this theory of Theia over the years, that you expect the moon to be made mostly of rock from Theia, but it's not. It's made mostly of rock from Earth.
Yeah.
And that was, we've covered this before several times, but it was Japanese scientists who figured out probably 4 years ago now, 5 years ago perhaps, that if the Earth was still a magma world with a lava world with a molten surface, then if that happens and something clouts it, then you tend to get the debris being part of the Earth rather than part of Theia. So it begs the question: how big would the Earth have been if it hadn't had this hit? I don't know the answer to that. You've got two.
Tested it.
Oh yeah, absolutely, yeah. It's just that I don't know everything. That's all.
Pretty close.
But you've got two conflicting things here. You've got the fact that a body has come along, hit the Earth, and in some ways combined its material with the Earth. But then you've got the negative side that some of that stuff's gone off to form the moon. So I think the Earth, let's see, you can't do a calculation because you don't know how much of that debris would have gone off into space as well.
Yeah,
it's not a simple checks and balances thing just because of the energy involved.
And
so the answer is I don't know.
What happened to Theia? Is it just part of us? It all got mixed up? Or did it deflect?
It's a lot of the debris. If you look at the simulation, I think I've got it on my computer somewhere, the simulation that these scientists produced for their theory, a lot of the Theia material disappears off into outer space.
Oh, wow.
There's a sort of movie that you can watch, and they've color-coded it with material from Theia and material from the moon. I'll have another look at it and see if I can deduce anything from that.
No, it's intriguing. It just prompts so many questions. I mean, obviously, because I've just been asking them all, but I'm sure it'll prompt some audience questions, because whenever we talk about these things, people just start formulating different thoughts, and some of them are amazing questions. So we'll see if anything comes out of that. But that's a really interesting story about the moon being older than we first thought, and you can read all about it in cosmosmagazine.com. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson. Let's take a short break from the show to tell you about our sponsor, NordVPN. Right now, believe it or not, I am on holiday with my family on the Gold Coast in Queensland, Australia. And we're staying at a place which is like a family resort, I suppose. Lots of things to see and do here, really geared for families and children. And of course, they have Wi-Fi, which is a public, unsecured Wi-Fi service. So naturally, you want to secure your access, and I've got my phone and my tablet secure with NordVPN, our sponsor, and it's been seamless. It's been absolutely perfect. I have noticed no slowing of speed, no problems whatsoever, and I feel secure that nobody can hack me. I'm not going to get spammed. I'm not going to have any problems, and I can do what I need to do, including the recording of this NordVPN sponsorship spot, and it's all going to go perfectly well. And it feels good. It feels good to be able to use a public Wi-Fi system that hundreds of people are using at the same time and know that no unscrupulous thing is going to happen. Now, as a Space Nuts listener, as always, we are offering you a great deal through our special URL. nordvpn.com/spacenuts. That's nordvpn.com/spacenuts will get you to the page where they've got a really good Black Friday deal going on at the moment. You can save big on NordVPN and get 4 extra months. And don't forget, there's a 30-day money-back guarantee. So a Black Friday deal for NordVPN. Once you go in, you can click on the button that says Get NordVPN, which I'll do right now because I've got it all set up through my own NordVPN service. And they have the 2-year plan, the 1-year plan, the monthly plan, depending on which way you want to go. The longer you go, the cheaper it gets month by month. And it is a really great deal. You get all the bells and whistles. You can get the whole lot in one fell swoop, which will cost you a lot less than if you bought it month by month. Secure high-speed VPN, malware protection, tracker and ad blocker, cross-platform password manager, which I found extremely useful these last few days while I've been away. The data breach scanner, the 1 terabyte of cloud storage, and the next generation file encryption. But have a look and see what suits you. And pick the plan that you want. You won't be disappointed. It is so very, very useful and seamless, absolutely seamless, as you can witness through the fact that I'm doing this on a resort Wi-Fi service through NordVPN. So, click on the link. Just go to nordvpn.com/spacenuts, nordvpn.com/spacenuts, and click on Get NordVPN and go from there. You won't be disappointed. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now we move a little way further out than the moon to a planet that no one ever talks about called Mars.
Well, it's your favourite planet.
It is.
That's why I thought we'd cover it again. I think it's a very nice story with a very nice acronym, SWIM. That's
SWIM, which stands for what?
The Subsurface Water Ice Mapping Project.
Oh, that's a good one.
It is because it's
SWIM.
It's where?
It's SWIM, really.
It's SWIM, yeah. Maybe SWIM's better, but they call it SWIM. And you can swim in water, and water is what they're looking for, but it's ice.
Now, so straight up, I'm going to ask you to dispel a myth or otherwise, but I always, growing up, was led to believe that the ice on the moon was all carbon dioxide ice. Not so by the sound of it.
Sorry, the ice on Mars.
On Mars, sorry. I keep doing that, don't I? They both start with M.
No,
the water, the ice on Mars was all carbon dioxide ice. I don't know why. I don't know why that was always a thing, but that's what I was led to believe as a kid.
I think you're right, and I think I would have said the same thing. I mean, I was a kid about 100 years before you were, but carbon dioxide ice, and it's certainly true that some of it is. Because we know that a lot of the frost that we see around the poles of Mars is carbon dioxide, because that's where the temperature gets low enough for carbon dioxide to freeze out, which, if I remember rightly, is around about 90, I think, minus 90 Celsius, 90, 85, 90, something like that. Can't remember the details. So there is definitely carbon dioxide frost in winter on Mars, and I think that's true mostly in the Arctic regions and the Antarctic regions.
Oh, okay.
But a lot more of Mars's ice is water ice, and in fact, a statistic that amazed me when I read it, and I think it's on a NASA page. So this was fairly authentic. This is quite some years ago. That if you melted the water ice just on the moon's south polar cap, you'd flood the planet to a depth of 10 meters or something.
Is that right?
Yeah, it's just colossal amounts of water. That's right. Yeah, and in a way that it's why we are so concerned about the polar caps here on planet Earth, because so much is locked away in there. If you start melting them all, you've suddenly got ocean sea level rise. We see it already in the Pacific Islands.
Well, Fred, I happened across a story this morning that there's one group of scientists that are saying it's too late. We're past the point of no return in terms of climate change on the planet.
The tipping point. That's right. And
that's
it's
the word
scary stuff.
Yeah, it is.
Yeah, it is scary stuff. Mars, on the other hand, it's got lots of ice, but it's locked up. And certainly people used to think that the poles were the only place where you do have water ice on Mars. But then many discoveries made since then, and particularly with, was it Phoenix, the spacecraft that sat in the northern Arctic, just a little platform, not a rover. This must be back in 2008, actually. It was a long time ago.
It's the one that used the backhoe to scrape the surface?
Yeah, that's right. A little backhoe to scrape the surface. And sure enough, within a couple of millimeters down, they hit ice. It's a permafrost there.
There's a famous photo of that. Mm.
Yeah, and there's one photo I sometimes show in talks when I'm talking about Mars that shows the scrapings on the day it was done, and then the scrapings 2 Martian days later. And you can see little scraps of material in the one where it's just been done, which are lumps of ice. And 2 days later, they've gone because they sublime. They go straight from a solid to a gas. They don't melt because the pressure's too low. And then, so that was really good evidence that it was water ice that you were talking about. But then it was analysed by the equipment on board Phoenix, and sure enough, it was water ice. So what the story is today with the SWIM project is because ice is really going to be such a major resource for future astronauts on Mars. That NASA thinks it's a good idea to have a map where we know we've found it. And they've used several different sources of data, including, many NASA missions, the Mars Reconnaissance Orbiter, Mars Odyssey, 2001 Mars Odyssey project, and now there's one called
Hello, this is NASA.
I can't even find my phone. It probably is NASA, yes, complaining. Hang on a minute. Sorry, let me just deal with this. I'll search.
I love that traditional old ringtone too.
Yeah. Ho hum, ho hum.
We also.
Yeah, sorry. I was. The trouble is, I can't even put my phone on silent because it also rings on my computer now because the two talk to each other.
Yeah, they do that, don't they?
There's no point in putting it on silent. There you go. Anyway, so yes, Mars Reconnaissance Orbiter, Mars Odyssey, and Mars Global Surveyor. And so what they've done is, they've taken all these data sets, and it essentially comes to a point where you identify the likeliest places to find Martian ice that you could dig up by future missions. And one of the things that they look for, this is a really interesting one as well, they look for recent impact craters on Mars because often if you have an impact crater, and it might only be, a few meters across because they can be resolved now by all these orbiting spacecraft looking down on Mars. Have an impact crater that's small like that. What it does is it blows away the subsurface soil and possibly rock as well. And what you get is an ice layer underneath. So you basically they can color code the surface to reveal the ice if from these impact craters. So they've used that as well to contribute to this map, the SWIM map that's been produced. It's worth a look for it. It's a NASA page. The headline is NASA is locating ice on Mars with this new map.
Yeah, is it going to be an actual map? Are they actually going to produce the map proper, or is this just what they're calling the project?
Oh, I'm looking at it.
Oh, are you?
Yeah. So this is. I mean, it's a work in progress, obviously, because it's a mapping project.
Oh, yeah.
Yes. If you go to that website, See, there's several versions of it.
I'm not like other people. I don't look at the pictures. I just go straight to the text. So I can,
of course, you would do that, right? As a radio broadcaster, you can't talk about things that people can't see, but we're doing it on Space Nuts. So. Okay, but really interesting. Little points where they've picked out these ice revealing craters. And so it's a work in progress. It's obviously going to continue. Very nice project, SWIM.
Yeah, I love the name of that. That's very clever. Yeah, I'll give them an A+ for that one, given how astronomers and space scientists tend to name things rather poorly. But that's a very good one. All right. Yes, as Fred said, if you want to chase that one up and learn more about the search for water ice on Mars, nasa.gov is the website, and you should be able to track that one down pretty easily through a Google search or anything like that. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
Hello, saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.
3, 2, 1.
Space Nuts.
Okay, Fred, you want to tackle some questions?
Why not? And I want to also just do a little recap of one of the stories we covered in a question a couple of weeks ago, I think.
Oh, okay. Yeah.
What was do you want to do that first?
Yeah, go for it.
Well, you might remember Peter, a.k.a. Toddy, asked a question about how the universe would look if there was no dark matter.
Dark matter, yeah.
And I've kind of waffled about it and said, I wonder if it would mean that because there's no kind of dark matter scaffolding in the universe to act as a gravitational sort of center for the hydrogen, if you wouldn't form galaxies. I wondered if it would not be possible to form galaxies. And so we have, and we were talking also about MOND, the modified Newtonian dynamics, which is an alternative view of the universe that attempts to eliminate dark matter. It suggests that at very low accelerations, Newton's laws don't hold, and you've got something else.
Yeah,
different accelerations, and we've got our kind of a secret route into the world of MOND, modified Newtonian dynamics, is young Peter Verweyen, who's a Space Nuts listener and a good friend, and he. I think I invited him in that episode to comment on it, and he has done.
Oh,
so,
very good.
Let me read what Peter says, which is it's great stuff. He says, "Hi Fred, That's a good start. I'm listening to the latest episode of Space Nuts, and here I am correcting you about Mond. With regard to Peter or Toddy's question, you were nearly right, but the wrong way round. Mond forms huge galaxies, far too large. So Peter's saying the theory's still got some way to go. He says simulations show that a universe ruled by Mond will consist of only a few huge galaxies with little or no other structure. This is because Mondian gravity is far too strong in regions of uniform density, just like just after the Big Bang. Voids form and are cleared too quickly, and everything collapses into truly massive galaxies and truly massive black holes and galaxies. And then he comments on the end, we're working on the solution. Good on you, Peter. Keep up the good work. It's great. That's so informative as well.
It is. It's great. Thank you. I think the solution would be blue tack. That would be, that solves a lot of things.
Yes, it does. Gaffer tape, maybe.
Yeah, we've got some of that too. All right. Well, that should solve Toddy's problem. Wrote to us a few weeks ago.
Well, it's the answer to the question, which was a great question, and that's what you get. You get big galaxies, which we don't have. Yeah.
Mm-hmm. All right. Let's move on to a question now from Paul.
Hi, Andrew and Fred. It's Paul here from Brisbane. My question is about how is the James Webb Space Telescope able to see galaxies that were 300 million years after the Big Bang? If we all started at a singularity, how could those galaxies have been more than 300 million light years from us, even if they were expanding away from us at the speed of light? And if they were only 300 million light years away, why have those photons not passed us long ago, even allowing for the expansion of the universe since then? It just seems like those photons have been travelling for a very long time, which must have meant that at the time that they were emitted, the galaxies would have had to have been further away than they appear to have been able to be, to me. Thanks for the show. Love your work. Bye.
Thank you, Paul. We get this question fairly regularly. It is one that is prompted by head-scratching moments. Hang on, how can they see that? How can they see something ancient when those photons are long gone? But it's not really that simple, is it?
No, that's right. And you're absolutely right, Andrew. We do get this question a lot. And Paul, I understand your frustration with not being able to, to get your head around it, because it's not that an easier problem. And of course, what you've just said, talking about galaxies 300 million years after the Big Bang, applies even more dramatically to the Big Bang itself, which we can still see. And that was, 13.8 billion years ago. We could still see the wall of radiation that was, basically the light of the Big Bang itself. It's now microwave radiation because of the expansion of the universe, but it's still there. So what I always advise people is to sort of forget about the idea that you're looking from the outside and seeing photons going past the Earth, because that's really not the way we look at this. The only way we can look at what we see is from our own vantage point, in other words, planet Earth. And the bottom line is, as we look out into space, we're looking further back in time. That's how all of astronomy, at least on these large scales, works. And irrespective of the expansion of the universe, which has certainly gone on, it's expanded, I think, about 1,300 times its size since the Big Bang, actually since the period of inflation, when it expanded a lot faster than that. So all we're doing is looking further and further back in time and seeing photons that are still coming to us from these ancient objects. And that's the way it works. And you're always going to be able to see that. To do that with everything in the universe, galaxies that are only 300 billion years after the Big Bang, you'll see those. They're in a sense in the foreground. They're actually nearer to us than the furthest thing we can see, which is the cosmic microwave background radiation, the flash of the Big Bang itself. And the light from that is still coming to us. And I think it's probably 2 or 3 episodes ago, in answer to a question from Rusty of Donnybrook, I gave that analogy about why we can still see the flash of the Big Bang. It's the cheering analogy, where you've got an audience of fans cheering a band and everybody suddenly falls silent at the same instant, but you can still hear the cheering coming from people around you. And it's the same with the flash of the Big Bang. My advice is always just think of it from our perspective. Sitting here on Earth, don't worry about photons that have gone past. Just worry about the ones that we actually receive, because that's all we can do is detect things from our own vantage point, and we still see those photons.
Yeah. I suppose to simplify it down to Andrew Dunkley level, is it basically a case of anything that's emitting light, even despite its age, is capable of being detected? Would that be a fair point?
Yeah, I think that's the bottom line. As long as it's within within what we call the observable universe.
Yeah,
and the observable universe is what we can see basically out to the flash of the Big Bang. We can't see, the universe goes on beyond that, but we can't see beyond that, because our look back time is back to 380,000 years after the Big Bang itself.
Okay, so that's just put another question in my head. How is it that we can't see? How is it that the flash of the Big Bang is not at the edge of the universe?
It's at the edge of what we can observe.
Yeah,
but
if there's more universe beyond that, how is that possible?
Yeah, because that flash of the Big Bang, that horizon, is in a sense an illusion. In fact, the best analogy is to where you were sitting on your cruise ship a fortnight ago or a week ago. I don't know whether you were out of sight of land, but if you were, all you could see would be a horizon around you beyond which you can't see. But the fact that you can't see it doesn't stop there being an ocean beyond that's hidden from your view. And that's the way the universe is. So the horizon, your horizon on your ship, is an illusion relating to your particular position. It's not the whole universe or the whole world. If you go somewhere else, you see the same thing, but it's it's a different vantage point. So the horizon's different.
I get it. Very good. All right. Thank you, Paul. Let's move on to our next question from Rennie.
Hi, this is Rennie Trout from West Hills, California. Always appreciate your shows. My question today is, when you calculate how long it would take to get to a destination like the moon or a different galaxy at close to the speed of light, do you take into consideration the expansion rate of the universe in that calculation? I'll be listening. Thank you.
Thanks, Rennie. That's a good question. I suppose it depends how far you're going, but even if you're traveling to the moon, do you have to calculate that sort of stuff in?
You certainly need to calculate relativistic factors in. You're not moving near to the speed of light, even in an Apollo spacecraft. Your speed's about 11 kilometers per second. So you've got to do things like relativistic time dilation and stuff of that sort, and the gravitational time dilation as well, which is kind of, both of those are on the scale of astronauts going to the moon are small, but they would have been taken into account in the navigation calculations. However, the expansion of the universe over scales like the 380,000 kilometers to the moon is totally negligible. So you don't start seeing any impact of that until you get to galaxies which are perhaps tens of millions of light years away.
Right.
And so far at the moment, we haven't got any way of traveling in those. If we had kind of wormhole technology that would let us get instantaneously from one bit of the universe to another. You would have to take that into account. You definitely have to take the expansion of the universe into account. But we haven't got that.
That would, if you travelled by wormhole, that would technically be time travel, wouldn't it? Because what you're seeing is ancient, but instantly getting there suddenly puts it in the present, and it's not going to be there anymore, is it?
Yeah.
You'd have to allow for that.
Yes, that's right. How do you work that one out?
I don't know.
Oh, it's gone.
It was here yesterday.
Yeah, that's it. Yes, well, that's right. Yes, absolutely. Yeah.
Mm.
Yeah,
it's a tricky one.
That one.
Yeah, that look. No, because we've had questions in the past from people saying, look, if you could travel through time, would you have to allow for the landing point on Earth to be in a different place because you're going there at a different time and a totally different era or whatever? It's not going to be where you left from, whether you're going forwards or backwards. It's going to be completely. Whoops.
Yeah, that's Geordie, our dog's spotted. He said, God, it really annoys me when he does that. It's usually, it's usually a cockatoo or something that's landed on the... He's in another room as well. He shrieks away. I've got to give him a good talking to about that. Yeah. He's only 6 months old, so I think it's something to do with that.
That's all right. So the answer to Rennie's question...
Lost your train of thought.
No, not really. But the simple answer to Rennie's question is yes. Over a long haul, you would have to allow for all of those contingencies, or you'd end up stranded somewhere. I mean, that's the bottom line, isn't it? It is. Yeah. See? Geordie's right.
See, Geordie agrees as well.
Absolutely. Okay, I think we covered that, Rennie. I don't know. I think we covered it. Yeah, I think we got it. So, yes, the answer is yes. Let's take a text question now from, I hope I get the name of this right, Man Soberg from Sweden. I love space, physics and astronomy, but sometimes when I listen and read about a distant object in the sky, I start to ask questions. And this is an old chestnut that we've been asked many times. Why is it important to know about objects that are a quadrillion miles away? How does this benefit me? I believe that this question is something scientists and astronomers around the world encounter every day, especially when trying to get funding. Why is it important, and how can this move humanity forward? Why should more people care about what happens outside our little blue dot? Bottom line, why is astronomy important? Thank you, Man. That is a great question, not an uncommon one, as you say.
That's right. So, and it is. And of course, astronomers need to know the answer to that question because they are, seeking funding. And in fact, let me just put it this way. One of the reasons why I got into science outreach, and this is now 50 years ago, when I started working at the Royal Greenwich Observatory, and realised that I was being paid from the public purse to do stuff that was not immediately beneficial to humans. So I had a moment of reckoning with that and thought, well, at the very least, I've got to be able to tell people about what we're doing just so that they get at least some interest from it. But of course, the answer is much more than that. I do remember a colleague of mine at the Royal Observatory in Edinburgh. I won't mention his name. And somebody said, so what use is astronomy? And he said, astronomy is the end product of civilization. And I thought, that's a bit arrogant.
That's big.
But I think what he was saying was, if you have a society that's kind of sufficiently evolved that it doesn't need to worry about the three main things, which are survival, eating and drinking, managing to sustain yourself and managing to reproduce. That's the kind of basic bottom lines of what life is about. Yeah. And in some places in the world, and we're reminded of that at the moment, that they're actually at that level. But for going beyond that, you might ask, well, what's the use of music, or what is the use of theatre? And astronomy sort of falls almost into those categories, but with some rather more significant aspects, because it is investment in astronomy in the past, and sometimes in the quite distant past, that allows our world to be like it is today. And the lives that we have are very much a product of some of the technologies that have actually arisen because of astronomy. And I'm thinking specifically, you hold up, remember that mobile phone that rang and interrupted us a few minutes ago?
Yeah.
There are 3 technologies in there which exactly like that, which basically the fact that they are there is what allows us to use them, and it comes from astronomy. So Wi-Fi was developed by radio astronomers to work out where the signals were going. The sensor, the image sensor in your phone, started its life in astronomical research. There was military stuff went into that as well, but astronomers actually pioneered the use of detectors to record images electronically at a very sensitive level. And the third one, which goes back 108 years, is that right, to 1915, general relativity allows GPS to work.
I was going to say
Einstein's great theory. And it was proven by astronomers. Astronomers had the wherewithal to demonstrate that general relativity is correct. We now live in an era where we use it every single day in the GPS in our phone. If you didn't have relativistic corrections, your GPS would be at least 10 kilometers out, and that is pretty useless if you're trying to find
very
a way
useless.
somewhere.
Yeah, especially driving around Sydney Harbour.
So the bottom line there is, what you're saying is that government investments in astronomy, whether they're in the academic sector or in infrastructure like the stuff I work in, is done with a view to, in a sense, protecting the future, or with an eye to what future developments might come from it. Now, we don't know what future developments might come from knowing, for example, that fast radio bursts in objects 8 billion years ago are being received today. But the physical processes that are going on in those fast radio bursts, astronomy stretches physics to its absolute limits, because the energies that are involved are usually far more than we could create in a particle accelerator on Earth. So it lets us understand the physical world in ways that we have no idea how that might impact on humans. We might have time travel one day, or space, or travel that at the moment is by means that we simply have never thought of, and a lot of that comes from astronomy. So that's one reason, and it's just the curiosity to see things that may impact one day on how we live our lives. Another is inspiration. It does inspire people into science. It's a great way of attracting kids into science, and it's one of the flagships of STEM education. If you can get 8-year-olds interested in black holes, and then you keep that interest up, then you've suddenly got somebody with a scientific mind, and who can basically see the benefits of how science works. All of that, education, inspiration. There are aspects of astronomy that do impact our day-to-day lives, and one of them would be if there was a potentially hazardous asteroid that needed to be observed by the world's most sensitive telescopes. You're going to want to know where it is and when it's going to hit the Earth. So all of those things conspire together to give governments an incentive to fund astronomy. We still have to work very hard on it. Astronomical funding is not great. I do remember a statistic I worked out back in 2000 was that the public money that went into the Sydney Olympic Games, is that 2000 it was, wasn't it?
Yeah.
The public money that went into those games was enough to run the whole of Australian astronomy for 100 years. And that just gives you an idea of what you're talking about in terms of budgets. It's probably, it's more than that now, but that at that time was the equation. So astronomy is actually pretty cheap compared with some of the other things that we do. Actually, there's another statistic that I quite often use, and that is, let me see if I can pull the numbers into my head. If you have a $2 billion project, and that would be the Extremely Large Telescope, that's enough to run the US military for slightly less than a day.
Yeah, that sort of puts it in perspective rather rapidly, doesn't it? Mm. Yeah. I think, Fred.
Go
on.
No, I was just going to say, what we're saying is that astronomy, whilst some of these numbers look big, and particularly in the space world, I mean, the European Southern Observatory's ELT, the Extremely Large Telescope, which has got that $2 billion price tag or thereabouts, is absolutely at the top end of what we in astronomy look at. Most of our budgets are way, way below that. And so that just puts it a little bit into perspective.
Indeed. I think you had people sold on mobile phones. If they couldn't have their mobile phones, the world would be in dire peril. So all you have to say is, well, if there was no astronomy, you wouldn't have a mobile phone. They'd go, oh, okay, yeah, no, I get it. No worries.
Yeah. End of story.
End of story. Total end of story.
Yeah.
Great question, though, and it's one that always comes up, and it's worth investigating, if you like, from time to time. Thanks, Man, and hope all is well in Sweden. If you have a question for us, please send it through via our website. We'd love to hear from you. Don't forget to tell us who you are and where you're from. SpaceNutsPodcast.com is where you can find us, and have a look around while you're there. Fred, we're done. Thank you so much. It was an enlightening program this week, for a change. Haha.
Yeah, full of life.
All right,
absolutely.
Thanks.
All right. Thank you, Andrew.
Pleasure. Thank you, Fred.
Great pleasure.
See you on the next episode. Fred Watson, astronomer at large, part of the team here at the Space Nuts podcast. And thank you to you for listening, and thanks to our patrons, of course, who contribute to the show. We really appreciate that. And you can do the same too through our website. And don't forget to keep those cards and letters coming in. And thanks to Hugh in the studio, because... And from me, Andrew Dunkley, we'll catch you again on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.